also be the demo that I give at the end, just because, again, the exercise will be based on a template that you will complete, but I think the demo will help to actually understand this template faster. So probably today, or hopefully today, the exercises go more smooth, also for the last one. Okay, so let's get into it. First, I will give like a quick introduction, what kind of problems we're actually targeting with this software tool. Then I'll explain like the general idea of code generation, a bit as a rehearsal about real-time iterations, even though already Moritz explained all the details, or in more detail than I will do. So it's more a summary. I'll give some application examples which are not really highlighting the most exciting examples. It's more like giving an idea of the computation times we're speaking of. And as I said, a short demo that is a very simple system we're going to control. Yeah, I'm sorry for people that did the spring school, the slides will look very similar. As an introduction, we're targeting not just linear systems, because if you think about it, like most systems you're interested in are described by nonlinear ODEs, as we had talks about simulation of nonlinear ODEs and DAEs as well. That's the main focus, let's say, of this software. So we want to not just study these systems, we want to actually control them or optimize parameters or optimally estimate the state that these systems are in, right? So they're all like similar optimization or optimal control problems, and applications are, very diverse. So the software, it's called ACADO, which stands for Automatic Control and Dynamic Optimization, so it doesn't come out of nowhere. It does actually stand for something, and the source or the whole code is online. If you look at the website acadotoolkit.org, you're actually redirected to a different URL, but this is the easiest to remember. And you will also find a link to our GitHub where you can file or report issues. You can find all the code and contribute to the project as well. It's all LGPL, so it's easy to incorporate in your own project. And also a nice thing, or at least hopefully you will be convinced of this, is that the user interface is quite user-friendly, or that's the idea at least. So it's a bit similar to YALMIP in a sense, but not exactly. Then, the code is all written in C++, even though we won't program any C++ today. And we will actually even export efficiency code, as I will explain in a few minutes. But as said, we will use everything from MATLAB, so we also have a MATLAB interface. And as it's C++ code, as long as you have a compiler, which might be the problem for some, you should be able to run this on Windows, Linux, OS X. We do support multiple platforms. So a bit about the developers. This is supposed to be the full list of people, main people contributing to the project, but probably it's not. Well, it's not at all complete. It's just the main people that started it are Joachim and Boris. So Joachim you already know. Boris is currently a professor in at Shanghai Tech, still working with ACADO, by the way. But I would say me and Milan were the most recent developers, even though Milan now also finished his PhD. So I suppose I'm now the main contact if you have complaints about ACADO or ideas for new features and so on. But the other people are still connected to this project for sure. So as a simple example, let's solve this optimal control problem where we want to make a rocket go from point A to point B, basically. So we have this initial states, basically a point, a certain position, velocity, and we have a certain amount of mass. And we want to get to this other point in an optimal fashion, so time optimal. So what we minimize is really just the time. Then we also have our model for the rocket and some extra constraints, which are just simple bounds. So as I said, the idea is to have a problem formulation that is as close as possible to this mathematical formulation. So if you put both next to each other, I hope you're more or less seeing the similarities. So we first have to define certain variables, of course, to actually form the expressions. So you have our differential states, which are, again, position, velocity, and mass. We have a control input u and a parameter t, which is the time we wanted to minimize. Now we just have to form some objects we will fill in basically. So it's a differential equation f, an OCP object, which we add the objective minimize t, and then we define our ODE in a way that is similar to the mathematical formulation. then we add all our constraints, like we want to start from this position or these states and end up with these states, add some bounds, and just ask the algorithm to solve the problem. The result, yeah, in this case looks a bit like this, but let's not get into details for this problem. It's mainly as a, an idea of how it works. So it's actually also a tutorial example. If you install ACADO, it should be somewhere in the examples in the OCP folder, I suppose. So as a list of problem classes, it's quite diverse. So yeah, as said, we treat mostly nonlinear optimal control problems where the dynamic systems are described by ODEs or DEs. So it's not so much BDEs, even though in principle you could try, but yeah, they're not specialized for this. So it might be that the solvers are not suited at all. Then there's also multi-objective optimization by the work of Philippe Logis together with Mattia, who was on my list of developers, by the way. They're from the chemical engineering department in Leuven. Then there's also like state and parameter estimation. Again, Philippe Logis with Dries Stelen. From the same department. Another important thing is, of course, nonlinear MPC. We have solvers for an MPC and environments to do closed loop simulations in ACADO as well. And robust optimal control, because Boris Huskin, one of the two main developers that started ACADO in 2009, his PhD topic was basically robust optimal control. So there's definitely support for that in ACADO as well. So this is what I will, in this talk, call standard ACADO, because the idea is that the solvers are written in C++ in a generic way. So you can definitely use them today, they're still there, but they're not designed to be directly used on your embedded system. And as our course has the word embedded optimization in it, it's not what I want to talk about now. What we want to talk about now is real-time MPC and embedded applications using code generation. So that's why my title was ACADO Code Generation and not just ACADO Toolkit. So I don't know if there's already questions, but that's it for my introduction. So a bit about this word code generation for those that are not so familiar, even though I think it already was used a couple of times by other speakers. If we have some mathematical formulation of our problem, we want to have some high-level interface. As I said, ACADO syntax is trying to be that interface. With behind that a lot of efficient solvers like the RTI scheme, using Gauss-Newton Hessian approximations, using, for example, QP-Oasis as the QP solver that can be warm-started, together with maybe condensing and multiple shooting and so on. So we have a lot of ingredients. This is definitely not a full list. It's just some examples of things you can choose from, in a sense. We want to put those things together and optimize code that solves exactly this problem. So it's, in a sense, like we want to instantiate a solver into C code like this, so really like line per line optimized code. That looks even more ugly than the forces code that Alex showed yesterday. So it's really specific for your problem. And then once you compile it, you can run it on your embedded system. That's the idea. And it's supposed to be fast, otherwise there would not be a reason to do this. Maybe one thing. So the idea is, it's a parametric optimization problem, right? So whatever you define as parameters, like your reference trajectories, your initial state is obviously a parameter in MPC. These things you provide online to your solver, which now is really embedded hardware, to get new decisions to be made, new estimates for your state, or whatever you optimize for. So as a summary, ACADO Toolkit, we want to solve dynamic optimization problems, parametric optimization problems, and I will talk about the code generation tool. So we have code generation tool for fast and MPC as well as moving horizon estimation. As I already said, the optimal control problems in both are similar, even though I don't think we covered estimation in any of the talks, but maybe I missed that. So it's kind of the dual problem. Instead of predicting forward and optimizing for the control actions, you would want to use your measurements, or at least a finite amount of those, and try to look back, in a sense, and optimize your current estimate based on all the information you have of the past. So MHE and NMPC go hand in hand because of the solvers being applicable to both problems. And we do this code generation from MATLAB today. So it's important that we have this MATLAB interface in which we describe our problems. So you could ask yourself, why are you doing this extra effort? It's another layer where you look at your problem and try to export code instead of just directly using your solver. The reasons are obvious, or at least some of them are obvious, that we want to optimize or make it faster. So we will look at the dimensions and already allocate all the memory instead of doing dynamic memory allocations. We would try to exploit certain problem structures. We would reorganize the code in a more optimal way and so on. Then apart from optimization, there's also customization. So in principle, you could really export code for your specific hardware. As said, this is kind of the workflow that we will be doing today. So this whole bubble is ACADO. It's all C++ code. What you're doing in MATLAB has, in a sense, not much to do with ACADO. It's just formulating your problem in a MATLAB syntax, which is then parsed into the C++ syntax. So you're just using it from MATLAB for convenience. Everything in MATLAB can be done in C++ and vice versa. Then we generate the code, so that's all C code, but we also generate max interfaces. Again, to make our life easier, these max interfaces are using the C code. They're nothing more than just a wrapper around them, such that we do the closed loop simulations in MATLAB, a bit like we did this morning, basically. So that's it for the code generation part, and maybe a bit, again, to summarize the algorithm, unless there's questions about code generation. Yeah, so I'll go quickly about this quickly through this, because I think Moritz captured it pretty well, but maybe the formulation is slightly different as he said it. So this is the optimal control problem we would ideally solve, which is not the most general case, because if you look at it, we already assume in continuous time that we have somewhat like a non-linear least squares objective, right? You see this function f popping up, but it's like the difference between this f and some reference trajectory. This y bar is something you give, like defining the problem, but it's in the square 2 norm. So it's a least squares form, which is very convenient because we have some algorithms like Gauss-Newton that are especially good for these kind of problems. Then in addition, there's much less assumptions in a sense, because we can have very nonlinear dynamics. We can even have DAEs instead of ODEs. We can have nonlinear path constraints and terminal constraints and so on. So in the constraints, we're less restrictive, let's say. So as said, it's a parametric optimization problem. So this thing in red, it's the initial state. It changes every time you call the solver, typically. And then this is the tracking MPC cost, as I said, and the nonlinear model. Maybe a short thing, we actually do have some development towards more general optimal control problems, more specifically because economic MPC is getting quite a hot topic. So if you're interested in that, there are definitely some interesting papers. Well, on the theory of economic MPC, but also in ACADO, there's some algorithmic developments going on to actually treat these problems. As said, you cannot use the Gauss-Newton method anymore for this problem, because in general, your objective can be anything now. So thinking of the kites that Moritz was trying to optimize, you would not want to optimize following this 8 thing. I mean, that's one way of dealing with this problem. Ideally, you just want to give, like, okay, these are my constraints. This is the model that I have for the kite. Now just optimize power given whatever constraints I have for the problem. So this minimization of power, which seems maybe trivial, I don't know, depending on your background, from a theoretical point, it's not trivial to still prove stability for this controller. But then there's the algorithmic side, which is not so trivial to actually still solve this problem in real time. So we will focus, at least in the course and in this presentation, on the tracking MPC formulation, which has this nice non-linear least squares form. Now we describe our problem in continuous time in ACADO, so we never use an integrator like the RK4 integrator that we've been using. We just pass the continuous time, and what ACADO will do for us is actually discretize it. So as we already saw, there's different ways of doing that: single shooting, multiple shooting. Direct collocation was mentioned as well, even though it's not part of ACADO for different reasons. But what we get in the multiple shooting would be a problem like this. So we really have this phi I as an integrator, but we never implement an integrator ourselves. It's part of ACADO. And we have this other discrete evaluations of our constraints and some discrete approximation of our objective. So in this case, it's basically just the sum of the least squares. So maybe a short intermezzo a bit about the integrator, even though you already know about integration methods from my talk on Tuesday, I think. So yeah, they actually already, I already covered Runge-Kutta methods and so on, which is what we use. And I already used this slide there even, so I don't have to say too much, but we do this evaluations of the simulation results, so this 5K with fixed step, Runge-Kutta explicit as well as implicit. We have to do that online now, so together with the sensitivity propagation. So the slides I had on Tuesday at the end where I talked about how to do it in different ways, that's kind of the topic, or at least it was a focus of me in the beginning of my PhD, to do that for different kinds of integration methods efficiently. So that's an important thing. Then there's also like model structure sometimes you can exploit. So actually in ACADO at the moment we allow people to say, okay, I have 20 states, but not 20 of them are appearing in a non-linear model, so that would be this one. So like most general case, you have an implicit DAE formulation. So this non-linear system in this case defines like these states x of 2 in square brackets. But you might have other states that are defined by partially linear dynamics in a sense, which are obviously much more simple to treat. Like sensitivities are constant, so you don't have to propagate sensitivities at all. If you apply an implicit method, you would not have to do Newton iterations for a linear system, of course. And also just the fact that they're completely, they're coupled, but they're coupled in one way. So like x2 has dynamics defined by x1, but not the other way around. So you just simulate one part of it and use the results to simulate the other part. So it's kind of, a one-way chain. So this really sped up, computations for certain applications. Then now we have a non-linear optimization problem, but we still have to, somehow solve that online. So for that, we of course use the RTI scheme, as I already said a couple of times. So it's sequential quadratic programming. So we do indeed, this is still the NLP. So we have these nonlinear constraints that you linearized this morning as well. We do exactly that. We use, even sometimes RK4 with similar sensitivity propagation as you did, so that we get this quadratic approximation of our problem, which at each time step we solve one QP like this, with the initial value embedding, so we get the nice properties of RTI, that it predicts basically, the next solution based on the change in the parameter. So this is, as I said, the task of the integrator. You do a simulation as well as a propagation of the derivatives, such that you get this AK, BK. And there's different ways of approximating the objective. So, but we will use Gauss-Newton because we will have least squares objectives, which compared to an exact Hessian method, for example, maybe I should state the advantages. If you don't remember, an important thing is in Gauss-Newton, first of all, you don't compute second-order derivatives. So you really only use first-order derivatives, which is already much easier to compute. And then you combine them in the way that you always get a convex approximation of your Hessian. It might be semi-definite, such that you have to regularize if your QP solver doesn't allow this. Like some QP solvers want strongly convex problems, such that you have to add this tiny regularization terms. But it will never be indefinite or negative definite. So this makes it easy to implement, fast and reliable in a sense. Then there's the other question. Now we have this QP. We already know how to implement the integrator, but how do we solve the structured convex QPs? For that, we already saw some solutions in a sense, like forces you saw yesterday. QP dunes will be covered a bit next week. HPMPC we won't really talk about, but you can definitely find some interesting papers on there. It's still under development, so you can find his code on GitHub, but I'm not sure how much tutorial material he already has. But I would look out for this one. It's very promising. But there's many. In principle, you could use any off-the-shelf QP solver. But as we started doing all this work to get things real-time feasible, of course, we want to look for the solvers, like the QP solvers that also tackle this problem as efficiently as possible. So the nice thing about structure exploiting QP solvers is that they usually, they should scale linearly with the size of the horizon, because they use, for example, a block Cholesky factorization instead of a dense Cholesky factorization. So they don't they don't have to, or yeah, they should scale in that way. Well, if you do condensing together with QP oasis, I mean, if you would solve the problem directly with QP oasis, that would be like the worst thing to do in a sense. As Joachim probably also mentioned a couple of times, it's a dense solver. You should not give this nice structure. So this is actually, I think, how the KKT matrix looks like. So it's really just a few non-zeros in a sense, like a small percentage of the whole matrix that contains non-zeros. So you don't want to just give this to QP oasis. We instead do the condensing to eliminate all state variables and solve a QP that is much smaller, like this one, but then completely dense. So we lost all sparsity, but we lost all sparsity by exploiting it in a sense. But this exploitation, instead of structure exploiting convex solvers, scales quadratically with n. So there's some interesting papers. I don't think I have the figures here. But I think Joachim had it, like these plots that show when actually one is better than the other. So it's really problem dependent. If you have a lot of states, less controls, and not too long horizon, condensing is usually the best thing to do. Once the horizon gets longer, structure exploiting solvers get better. And then if you get a lot of controls, condensing might also not be such a good idea. I mean, it's obvious that if you have a lot of states compared to the controls, it's good to eliminate them because you suddenly got rid of this huge dimensional space. And as said, this small dense QP, we in ACADO at least solve with QP oasis, but now you could actually solve this with any QP solver as well, because you don't even rely on sparse linear algebra, because you don't have a sparse problem. Then a bit about the RTI workflow. This is in a sense a summary of Mort's talk, but then in the least mathematical way of saying it. So we have initial value embedding, which means that we have this parameter always linearly appearing in our problem, which means we always satisfy the initial value constraint because we do full step SQP. So this initial value embedding and the QP solution form the feedback step, while the integration and sensitivity generation, let's call it just linearization of our non-linear problem, together with possibly the condensing. Condensing might be there, might not be there. That's what we call the preparation step. So if you look at it, we would prepare the QP before we even know the state, right? That's the idea of preparing all of the data. And then once we actually know the state, we would just embed it in our problem and solve it. So we get this quick feedback while, because we expect the linearization to be kind of costly compared to the full iteration. So this is a loop that goes on forever, as is the case when you want to control a system. So a bit more in depth if you would look at it. Once you get your measurements, so that's this tiny time block, so it's some delay that you have from getting the measurements. You would give those measurements. So this is the case where we actually have an estimator as well, and it's even more specific. The estimator is doing MHE using ACADO as well. So the estimator would have also like this feedback step, basically to get the next estimate. So it's again a small step or a small block because we want to just solve the QP. We don't have to linearize anything anymore. And then once we solve that, we have the X0 or the estimate of our current state, which we just pass to the feedback step over the NMPC. So it's like supposed to be short delay, so get the measurements, get the state estimate, and now here we have the control which we apply. So here we actually solved our problem in a sense, but now we have to know, okay, how can we do this the next step again, which is the preparation step. So once you did this feedback step of the MHE, you can already start preparing the QP for the MHE problem. And the same here with the NMPC. So in a sense, you can even, this goes on forever, of course, and it should end within this time window that you have. You have a fixed sampling time, and we try to keep the solvers as deterministic as possible, so you can look at the worst case time and make sure that everything finishes before you have the next measurements coming in. And these two things can be in parallel as well. Even though actually these preparation phases can be parallelized as well. So that's, there's many parts of this algorithm which are parallelizable. Then as promised, a few applications, even though I won't talk too much about them, I just want to show a bit the variety of problems and the computation times. So this is the problem that, or the project that Moritz already mentioned many times, I suppose, or at least a couple of times, namely the Highwind project. And actually the picture is from Leuven, it's not from Freiburg, even though we have a similar carousel setup now also in Freiburg. And I think this is work from Milan mainly, that he had both MHE and NMPC running in real time as the video was showing during Mort's lecture. So a bit about the dimensions. He had 22 states and 3 inputs in the model. Yeah, some various measurements. There were still camera measurements and IMU measurements where the IMU is at a very high rate. So they had the problem of actually, bringing those into the grid that the optimal control problem was solving. So the sampling frequency is 10 Hertz. I don't know how long the horizon was back then, but they somehow had to bring all these measurements into the problem framework or the problem formulation that they were solving. And some encoder measurements, so like different measurements coming in at different speeds. And both the MHE and NMPC were implemented with ACADO, so following the same RTI framework, doing quick feedback and preparing for the next QP. And these are the worst case timings as well as the average, even though they don't differ so much in this case. And I think as they had 10 Hertz, so 100 milliseconds, it was fast enough such that they even did multiple iterations, as I remember, at some point. So that's not the idea of RTI. Like, ideally, if your system is very nonlinear, like the kite example, you just want to sample faster if you can. So if your system allows it, you just want to be faster, then you get disturbed in a sense because you're converging your algorithm over time. So yeah, by being faster than your disturbances, you will never get unstable. That's the idea. Another example is, again, MHE on an induction motor. So this one is a bit older than the kite data I have even. But here they actually used like an embedded system. So it's a nice example that it doesn't always have to run on like your high-end desktop that you have running. Like they actually used the DSP here. Only 1 gigahertz, and the sampling frequency was actually 1.5 kilohertz, so they had to be fast as well. So they didn't have the 100 milliseconds. But it's, of course, like a much smaller problem, like 6 estimation intervals, 5 states, and 2 controls. So it was small, but that's exactly what ACADO, definitely at that time, ACADO was, or ACADO code generation was dedicated to these smaller problems. Now we can scale it up a bit more. And a last example, which is actually the crane that I think was also on Monday in the introduction lecture, where I mainly wanted to show the structure. So we had 8 states, but 6 of them were linear input states. So that's where the idea came from, actually exploiting the structures, such that if you check like the integration time, I think it's speed up factor of 3 in this case, but we had more interesting or more challenging models where the speed up factor becomes even bigger because this is still a state space of 8 and not too big. So I think if there's no further questions, I will proceed with the live demo. Yes. Mm-hmm. Yeah, so the idea is basically the asymptotic complexity of how they scale with the horizon length, right? I mean, there's more to it because they also have different complexities of how they scale with the number of states and controls. And then even the structure exploiting solvers have different ways of scaling with that. But as a general rule, you could take what Joachim had, where I think he said as long as the horizon length is much larger than the ratio of states and controls, then it's better to use a structure exploiting solver, which basically means that condensing RQP bases is better if either you have a lot of states compared to the number of controls and not too long horizon length, or you have not too long horizon length in general and a fair ratio. No, this is, I mean, these options, they're not optimally chosen in a sense. So that's what the user has to try out for different problems. Because the only way to find out really is to use the solver and see how fast it solves in simulation. Well, the ones I mentioned, yes. Yeah, but there's definitely a few that are not interfaced yet. But these like Forces, HPMPC, QPDunes, they're currently interfaced for the problems that they're currently solving. as they are also under development, so some constraints you have might not fit the current interface and stuff like this. Yes. No, that's a very good point. So the condensing could be written such that it's exploiting the structure, which we didn't yet. That's a very good point. No, I think it would be a bit tedious, but definitely worth it for bigger problems. Exactly. Yeah. Also, depending on the algorithm, it might be easier for But that's definitely true. Yes. Other questions? Then let's look at the code. So the demo, it's the van der Pol oscillator, so I really just have 2 states and 1 control, which will make my life easy to actually visualize the things that are going on. So I really just want to quickly go through how the code looks, even though you will do probably the same once you get the template in front of you. So as I already had on my slides as well, we first always have to define the variable. So in this case, I just have 2 states and 1 control. So this differential state, it's an ACADO keyword. The moment you use it, ACADO is, let's say, triggered as, okay, there's someone in the, you're defining a problem, and it keeps track of all the things you define, all the equations, the OCP objects, and so on. So yeah, once we have these variables, you can use it. So I could run only this section maybe. So now I have x1 and u, so I can form expressions like x1 plus x2 and start accumulating all of my expressions like that. Then dot is also an ACADO keyword, so it's the time derivative of x1 equals this expression. Similar to YALMIP, I can use this double equal sign. And these are my dynamics, not too special. I want to do a closed loop simulation, and again, it's going to be like this ideal case where my model is the same in a simulation and in the OCP, just for the tutorial sake of simplicity. So I will also use SimExport, which is an ACADO module that exports an integrator, just simulating your model, similar to, I think it was an extra of the first or the second exercise, to use this instead of the RK4 integrator in a sense, because it will have very similar to maybe even exactly the same interface, as you will see. So the SimExport, I won't explain too much. In a sense, it's just you define the interval on which you want to simulate, so it's all fixed, so you can just use TS as your sampling time. You set the model, specify the integrator, so that's the integrator type. I pass the option and specify, for example, an implicit Hungokuta method of 4th order with a fixed number of integrators, integration steps. Then I specify the model folder where I want to copy all files, just to know where it is basically, such that afterwards in this folder you can find the make ACADO integrator. So make ACADO integrator is a script that is automatically generated for you, like you don't have to, as you can see actually, shit, I think I'm in the wrong folder, aren't I? Or I don't know. Yes, sorry about that. So it's just in time before the error would appear. So now I can run this section, which is gonna export all the codes regarding the SimExport, so the simulation environment in a sense. So now I have the make script, as I said, is auto-generated. So if you look in this export sim folder, all files here automatically appear there by calling ACADO, so I don't have to change anything here. And the make script automatically compiles all these files together as well. So once I did that, I have the integrate VDP, which, for example, I can call as the same as the RK4 integrator that we used. I can specify a state where I want to start from, control that I would like to apply, and now I can do output is integrate VDP. Integrate VDP is just the name that I chose, so you can call it whatever you want. And of course, I'm in the wrong folder again. Yes, so this gives exactly the same interface as we had so far. So it has the value, sense X and sense U, because it propagates sensitivities. There's options not to have the sensitivity propagation, but as we are usually interested in integrators for optimization, we need differentiable objects, so we need the derivatives as well. So if you check the value, yeah, something that is not a number at least. So this seems to work. Let's formulate the OCP as well. For this, we have to define our horizon, of course. So this big T is, I think, yeah, 10 seconds in this case, and I have 20 intervals. And I have to define my objective, which is this least squares cost. It's a simple one. The first argument is the weighting matrix. I just chose identity. And the second argument is a residual. If you remember this function f, which needed to be minimized in the least squares term. That's this one. It's not a non-linear function. It's just a concatenation of my two states and the control. And then I also have a terminal cost. So that's the minimize LSQ n term, the terminal term basically. And LSQ stands for least squares. So that's it for the objective. And then I have some constraints. So subject to basically is all constraints you have. So in this case, I also set the model. I have some bounds on u, so similar syntax to YAML. And this at end means that it's only at the last node, where I say that I want both states to be equal to 0. So it's a equality terminal constraint. Then I have a lot of options, even though this is only a few of them. So the Hessian approximation I specify is Gauss-Newton, but I cannot really choose anything else here because it's least squares cost. Discretization, I choose multiple shooting, which is a good idea always. And I will do condensing. So it's full condensing n squared. Full means I also eliminate the initial state. And n squared is just specifying which algorithm it's using. Then integrator type, it's the RK4, same as we used so far. I specify the number of steps equal to the number of shooting intervals, and we use QPoasis together with the condensing. So once I have done that, I will again just export the code that is in this MPC object and use the make ACADO solver, which is auto-generated. So let's run this section. This is this part, which looks almost the most complicated in this part, is actually just copying the QPoasis solver, as I'm too lazy to do this in front of you. And maybe failing at actually finding the QPoasis folder. You always have to copy your solver in there somehow, because you might be using QPDoons and forces and so on, and we don't provide the solver together with ACADO, depending on which solver it is actually. So it's always a good idea if you get some weird error to check if your solver is actually in the export MPC. So if we check here, QPoasis, as we copied it in there, is in this folder together with a bunch of auto-generated files. Maybe at this point it's even interesting to check what is in these files. Like first of all, it's some licensing. It's the ACADO toolkit, which is distributed without any warranty, so we're not the reason your system might fail. So we're not reliable. Then these are some right-hand sides and so on. And this is the very ugly code that I talked about, which is in this case still rather simple because it's RK4 integrator. Then we will do the closed loop simulation. So I have my simulation routine and an optimizer. So I can just connect them in a simple simulation as we did today. So I will choose I will simulate over 20 seconds, start from 0, 1 as the initial state. Here I initialize all my trajectories. So input.x and input.u will be my optimization variables. So the state trajectory and the control trajectory. And then y are the references. So it's like you want to minimize the deviation of your states and controls with respect to this reference trajectory, which in this case, we're just controlling everything to 0. So it's a trajectory of all zeros, basically. You will do the same in the exercise with the pendulum, basically minimizing everything with respect to the upward position. Now, okay, so maybe I should run this part as well so that I don't run into problems. Then the simulation loop is rather simple now. So the main parts are this, where I actually call the MPC controller. So ACADO MPC step is how I called it here. You can call it whatever you want. And it has the same structure that you just provide an input structure and an output structure comes out of it, where all the fields are the things you have to set, like the state trajectory, control trajectory, because you always have to initialize it somehow. The initial state, reference, weighting matrices if you specify them as parameters, and so on. So if you don't provide the correct one, the max interface is written such that it will complain either about the dimensions or a field missing. So hopefully that will help you as well. I will actually already do the shifting, even though you can ask ACADO to do that for you. And then the other part is to actually apply the control to the system, which we do, of course, separately, because you might want to simulate model mismatches, or you might want to simulate some disturbances popping up, which I will do as well, actually. So the integrate VDP is this simulation routine that I exported. So that's it, because this is just for plotting. And here I have some output on the computation times. So again, I went into this folder, which I should not do. And this is the first step. So what we did now is really just start from 1. So it's 0 for the first state and 1 for the second state. And we already did one step. So I asked ACADO to optimize given 0s for all states and 0s for the controls, given the initial condition that is 0, 1, as I just said. So already now, we got some kind of trajectory, even though we just did one iteration, so it's one linearization and one QP solve. But if you check, sorry, if you check actually the trajectories, so like the crosses are the trajectories, or like the points that I get out. But if you would simulate, so if I use these control values to simulate from one point, so 1x to the next one, I see that the simulation doesn't quite get to this next point in a sense, right? There's these gaps popping up, which is exactly what multiple shooting does. It defines that the next point is equal to calling your integrator on the previous point using the control. So these gaps are these non-linear constraints are in your NLP. And one SQP iteration is simply not enough to get completely converged, of course. That would be, very nice if that was the case. So we don't have a fully feasible trajectory, but still we just apply the control input blindly in a sense. So that's the idea of RTI, to just do one SQP iteration. But as I said, we do the shifting such that this whole trajectory now becomes the initial guess for the next iteration. So if I do one more iteration, so I just, I had a pause and now I unpause it for one more step, and I again do the simulation, you see that it's already much, much better. So it's not, you barely see any gaps anymore, actually, to be honest. So I suppose if I zoom in enough, you see that there's indeed still a gap, even though this looks like it's a gap from the plotting and not from the actual accuracy. But of course, it's not converged up to machine precision, but it looks already very decent. And if you check the closed loop, so what you see actually in light blue and light red, in a sense, is what I predicted would happen. And what is in very bold, that's what is actually happening. So you see everything is matching quite well. And I think at 8 or 10 seconds, 10 seconds, we just add some random disturbance just to see what happens. So we randomly added 0.8 to our second state. And if you check again, we disturbed our convergence such that indeed we have these gaps again. But by keeping the solution trajectory and sampling fast enough, we converge over time. So this is illustrating both how ACADO works and how RTI works quite well, I hope. And then if you check the computation times, it's around 100 microseconds for this case. 200 microseconds for the first one. It's a bit random because it's on my laptop and it has a lot of other things that it might prioritize for some weird reason. So it's not real time and as deterministic as it could be, but it's quite fast, even though the system is, of course, also very small. So are there any questions, or is everybody ready for doing this on the inverted pendulum? No questions? Then I think, did I stop too early or too? It's 3. And we start normally at 1:30, right? So basically, it's perfect time for coffee break, no? Thank you.